So in the second part of the section 5.1 content, we're going to be doing a couple of different examples. Now it's kind of hard to do every single possible example you'll ever see with trig identities because there's just so many different ways to rewrite it, and there does tend to be a bit of creativity involved in solving these. So we'll see a couple of common ones. I'll give you kind of a common method on how to simplify them. But at the end of the day, you're going to see some probably that might not look super familiar, and you'll just have to try to figure out a way to solve it. I still have here, though, the three sets of identities, so hopefully you have those close at hand because we'll be using those throughout today's lesson. Okay, so the first example, there's going to be three examples in this one, but the instructions will be the same. It's going to say simplify the trig expression. So you'll have something involving trigonometric functions to a single trig function with no denominator. I should say denominator equal to 1, but no denominator is essentially the same thing. This is a really common instruction, and so you'll see this in Delta Math quite a bit. All right, so let's start off with one that looks relatively simple. We'll see how much work it requires, but it's going to at least look relatively simple. So we'll say we have sine of theta and then secant of theta. Now, a lot of times you'll see it written this way. I like to actually put parentheses around my thetas to recognize that the theta is with the sine, and then there's a theta with the secant. They're the exact same theta. They're not different in any way. So this is going to be, we're going to be using identities to solve this. Okay, so a great first step in pretty much every single problem you come across, not always, again, there's going to be exceptions, but most of the time is to convert all functions, all trig functions, to sine and cosine. So using the reciprocal and quotient identities, you can actually convert every single trig function into a function involving only sine and cosine, expression only involving sine and cosine. So let's start off here. Sine is already in terms of sine, so I don't need to worry about that. For secant, if you take a look at the reciprocal identities, you should see that secant is actually 1 over cosine of theta. Keep in mind that's a multiplication there. Now this almost looks worse because I went from no denominator to something with a denominator. But let's go ahead now and multiply. So sine of theta is really sine of theta over 1, and then times 1 over cosine of theta. To multiply fractions, you just go straight across here, so I end up with sine of theta over cosine of theta. Now everything, there is still a denominator here, which isn't great, but let's take a look at our quotient identities. So let's take a look at the quotient identities. And you'll notice that sine of theta over cosine of theta actually equals tangent of theta. And so we've gotten to a point, there's no denominator, and it's only one trig function, it's just tangent. So that means that we're actually done with this problem. We solved it. Okay. So that one was maybe relatively straightforward, although it is still a little bit weird if you haven't done this stuff before. Let's try out another one. Let's do sine of theta, and then we'll do cotangent squared of theta plus 1. Okay, so this one's a little bit weird because there's sine of theta and then there's this cotangent squared stuff, and we don't really know what to do with that maybe. I said that a great first step is to convert all functions to sine and cosine. I'm actually going to tell you to pause just a moment here. If you see squareds and then adding, there's a good chance, again, not always, there's a good chance that this means we're going to be using the Pythagorean identity. So let's take a look back at our notes from before, and let's see if we can't find a Pythagorean identity that might help. So hopefully you saw one of the versions, I think it was the second version I wrote down. Cotangent squared of theta actually equals, so this, sorry, cotangent squared of theta plus 1, all of this actually equals cosecant squared of theta. So now I have sine times cosecant squared of theta. Now that I've used the Pythagorean identity, I will go back and use that first step, which was to convert to sine and cosine. And so I'm going to use the reciprocal identity to say that this is actually times 1 over sine squared of theta. And I kind of knew to do that because I remembered that cosecant was related to sine, so I'm hoping there's some cancellation that happens here. By the way, I should be using more parentheses. I really try to be consistent with that. Okay, so once again, multiplying, we get sine of theta over sine squared of theta. Now there's one sine of theta above and it's a sine squared below, so we're going to cancel those or divide them. Sine of theta divided by sine of theta gives me 1 in the numerator. Now I do still have a denominator. I have one, I'm down to one trig function, so that's good. But I still have something in the denominator. So I'm just going to use the reciprocal identity again to kind of go back the other way and say this is just cosecant. And so now there's no denominator. Okay, so this one was a little bit more involved. We had to recognize that there was a Pythagorean identity occurring. And then once we did that, we were sort of into the same situation as part A, which was converting to sine and cosine, and so we used the reciprocal identities a couple times throughout this problem. And now we have simplified this expression. Let's do one more of this type of example. So we're on part C. And for this one, we're going to do something, we're going to kind of ramp this up a little bit more. We're going to do some adding. So I'm going to do 1 over 1 plus sine. I'm going to switch to x because you see x is a lot as well, but it's the same as theta. It doesn't really matter. And so we're going to add these two fractions. Now, one thing we should probably do at this point is review how to add fractions. So recall that we need a common denominator. And if the denominators are different, this actually means that we have to multiply them together, multiply the denominators together. Okay, so here's what I'm going to do. I'm going to take my 1 over 1 plus sine of x, and I'm going to multiply that. Let's put parentheses around it so I don't forget. I'm going to multiply this by 1 minus sine of x over 1 minus sine of x. And then I'm going to add 1 minus sine of x, and now I'm going to multiply this by the other denominator, which is 1 plus sine of x over 1 plus sine of x. Okay, so let's go ahead and kind of clean this up a little bit. Here we have 1 times 1 minus sine of x, so that's just going to be 1 minus sine of x. Over here, we have 1 times 1 plus sine of x. So I'm going to be adding 1 plus sine of x, and then all of this is going to be over the now common denominator, which is 1 plus sine of x times 1 minus sine of x. The numerator we can kind of clean up a little bit more. 1 plus 1 gives me 2. Negative sine of x plus sine of x is just 0. So I have 2. Now in the denominator we might need to do a little bit extra work. So I'm going to just show you real quick what this comes out to. If I have 1 plus sine of x times 1 minus sine of x, we would do 1 times 1, which is 1, minus 1 times sine of x, and then we're going to add a sine of x times 1, so those will cancel out to 0. And then we're going to subtract sine of x times sine of x, which is sine squared of x. So those cancel out to 0. So I'm left with this in the denominator. If you kind of want to skip this step, you can. This is going to come up so often where you have 1 plus a trig function times 1 minus a trig function. It's going to come up so often that if you know the answer and want to just skip it, that's okay. All right, so now we're kind of stuck because we have a denominator. We only have one trig function which is good, but we have a denominator, which is not good. And I can't just pick part of the denominator to take the reciprocal of and move it up. So we can't just pick the sine squared out of the denominator, because it's actually 1 minus sine squared. It's not just sine squared. So we're going to actually use a trig function here. Notice that I have this squared and I have a 1. You should hopefully start thinking about the Pythagorean identity. At this point, whenever you get stuck and you see a squared, start thinking about the Pythagorean identity. So if we go back to that, if you take a look in your notes, the Pythagorean identity says that sine squared of theta plus cosine squared of theta always equals 1, no matter what theta is. Well, that tells me that cosine squared of theta must equal 1 minus sine squared of theta, right, if I subtract that over to that side. So that means I can actually go back to what I was working on and just rewrite this as 2 over cosine squared. Notice we're using x, not theta, so just be careful with your variables. But this is actually 2 over cosine squared of theta. Now notice all we have in the denominator is cosine squared of theta. So I can actually reciprocate this now, take the reciprocal of it. I don't think reciprocate is a word in this case, in math. So I could actually move the cosine squared up by using its reciprocal function, which is secant squared of x. So notice now that I have, even though there's a squared, I only have one trig function. You know, I think I'm going to just kind of break this up here because I have some scratch work off to the side and I want to sort of make sure that makes sense. So I have one trig function. I also have no denominator. And so that means I'm done. This would be my final answer. Okay, so let's just kind of recap. We did 3 examples of increasing complications, complexity. So we simplified the trig expression to a single trig function with no denominator. The first one was basically kind of one step reciprocal rule and then a quotient. I guess that's 2 steps. The second one took a little bit more work because we had to use the Pythagorean identity, followed by the reciprocal a couple times. And then the third one, what made this one so complicated was that we were adding. So we had to first use a common denominator to add them together. And then we use the Pythagorean identity followed by this reciprocal. And that ends this video. In the next video, we'll see a couple more examples, a little bit different.